students. It's an electromagnetic induction exercise. I think LS can benefit from that too, but it's a little bit hard. I don't think it's LS level, it's GS level, and maybe it's one of the toughest problems we got in the official exams. So let's roll. So in this exercise, we have a spring that is connected to a rod Mn. And as they said in the given, the aim of this exercise is to determine the magnitude B of uniform magnetic field. And we consider a spring of stiffness K, negligible mass, attached from its upper to its upper end to a fixed support. Its lower end is attached to a copper rod Mn of mass M and length L at equilibrium, and this is a key word here. At equilibrium, that means we have all the forces equals to 0. Okay. The elongation of the spring is delta L0, and the center of mass G of the rod coincides with the origin O of a vertical x-axis of unit vector I. So we have an x-axis that is going vertically downwards, okay? And if we have anything that is going in the opposite way of that, it's considered negative. So in question 1, part 1, we have the rod in equilibrium. Name the external forces acting on the rod at the equilibrium position. I think that's really obvious, and it's more like grade 9 type of question. We have a spring, and we have something that is attached to a spring, no matter what it is, a sphere, a solid, a rectangular solid, or a rod Mn. We simply have the weight of the rod Mn that is going from the center of gravity of this rod Mn vertically downwards, and we have the spring doing an opposite force going upwards to keep this rod stable, to keep it at equilibrium. Okay, so simply in question 1 we can say we have two forces. The weight of the rod, Mn, and of course the symbol of the weight is W with a vector, and we have the tension of the spring, which is trying to hold the rod upwards. See. And let me remind you of something. When we have the tension of the spring, we can talk about Hooke's law. Maybe it's forgotten by way too many students, but it's really important every time we see a spring. So this is 1.1. Now 1.2, they're asking to determine the relation among MGK and delta L0. Okay, now the title of part 1 is the rod in equilibrium for a reason, because they're telling us that we can use this expression here, sum of the external forces equals to 0. So I can start by that. Now you're asking me why did you think about this part? Because they want a relation between M and G, which are the things we use for the weight, and they asked about K and delta L, which are the things I literally just talked about for Hooke's law, which is T equals K delta L. So it's T. Now, how am I going to relate these two? By using the sum of the external forces. So, at equilibrium, the sum of all the forces is equal to 0, which is obviously the tension and the weight equals to 0. Now, if we project that on the x-axis that we have going vertically downwards, we will be getting minus T and plus W, because T is going upwards in the opposite direction of the axis, so it's minus, and the weight is positive, equals to 0. And by the way, you have to mention that you remove the vector by using the projection condition. So let me take this here and state on the side that projecting on the x-axis, and then we can remove the vectors. Sometimes people forget what projecting actually is. When I tell you you have the tension T, I mean you have the magnitude of T that is going along the direction of I. Okay, it has the same line of action as I, but it's going in the opposite direction of I, so we put a minus. When I say project the forces on the x-axis, that means multiply or find the dot product of the force with the x-axis or the unit vector that represents the x-axis. And when you multiply two unit vectors, the same unit vector, you will get a magnitude that is equal to 1. This is why we remove the vectors and we will only be keeping the magnitude that we have with the sign. Okay? So this is it. When we say projecting, it means find the dot product along the unit vector of the axis we're working on. Now, what do we get? T equals W. That means T, using Hooke's law, it's K delta L. And since they mentioned specifically in the given that we call that at equilibrium, we should call the elongation delta L 0. So I have to respect that. Delta L 0 equals to mg. And this is a relation between these four quantities. It's a grade 9 level, but sometimes grade 12 students forget about that. So here's your reminder. Now, in question 2, we have the electromagnetic induction. The rod Mn may slide without friction along two vertical metallic rails P, P prime, and Q, Q prime, as figure 2 shows here. Okay, so we have a capacitor. We have this rod that is placed on the two metallic rods P, P prime, and Q, Q prime, and we're supposed to slide that without friction on the metallic rod. Okay, now, during sliding, the rod remains perpendicular to the two rails. The two rails are separated by distance L and the capacitor, initially uncharged. So the voltage of the capacitor at the beginning, it was 0 volts. Of capacitance C is connected between P and Q. Neglect the resistance of the rod and of the rails. So there's no resistance, no friction. There's no need to include it in our calculations. Now let's continue the given that we have for part 2. This setup is placed in the region of a horizontal uniform magnetic field B perpendicular to the plane of the rails. So the magnetic field, obviously, as the figure showed in document 8, it's going inwards. When you have a circle with X, that means B is going inwards the screen. It's like you're targeting your pen into the screen. Okay, when you have a circle with a point, that means you're holding your pen in the other way around and it's going out from the screen. Okay, so here we have the B going down into the screen. Okay, let me continue my given. At the equilibrium position, V is found at a distance D from PQ. Okay, so we have the distance of the rod from PQ, which is D. The rod is pulled vertically downwards from its equilibrium. Okay, so I had an initial distance D, and we're moving the rod vertically downwards, so we're actually decreasing this distance D. So we had Mn at some point. Oh, it's D, it's mentioned, yes. This is what I should have drawn from the beginning. We had a distance D, and it is reduced by a small distance X because we're moving the rod downwards. So we're actually decreasing the surface. Okay, so you have the surface like this at the beginning. Mn was here, and this is the distance from here to here, it's D. But when we pull the rod downwards, we decrease the surface by amount of X. So actually here we'll be having to do D minus X to find the length between PQ and the rod that we have. Usually they give it as addition, D, and they add a distance X. Now here they're removing from the distance X. Now, so we mentioned that from its equilibrium position by this distance xm. So we're pulling the rod Mn, and by pulling the rod Mn, we're actually pulling the spring. Okay, so to a distance xm, and when we release it, the rod will start to oscillate with the spring. Then it is released without initial velocity. So what does that mean? The speed at the beginning of the experiment was 0. We release it without speed. And at this moment, the rod wasn't at 0, it was at xm, the maximum distance possible. Thus, G oscillates about its equilibrium position. So this is O, okay? We pull the rod by a distance xm downwards, then we leave it to go up, then down, then up, then down across O, okay? About its equilibrium position O. At an instant t, G is defined by its abscissa and the algebraic value of its velocity is, okay. Taking the positive sense shown in document 8. So the positive sense of the current is going from Q to P to M to N, like this. Okay, this is the positive direction we chose. Uh, show that the expression of the magnetic flux we mean phi, crossing the area MNQP is given by flux BLD minus BLX. That's really easy, but because the electromagnetic induction, it literally has about two formulas and that's it. Flux equals ND dot S. Okay, or you can label it as N S B cross N, and N is the unit vector of S. Okay, or you can say N is the normal vector of S, of the surface S without a vector. Because every time you have a surface, by the way, the normal vector or the unit vector of the surface vector should be perpendicular to the surface itself. So this is S. Even though S is horizontal as a surface, its vector is perpendicular to it. So N is always perpendicular to the surface we're working on. So this is your first formula. Your second formula is E equals minus d flux over dt. Okay, which is Faraday's law. And you have Lenz's law, which is a sentence you have to explain. And it's a chain that I would mention if I had this in this problem. If it doesn't pass by through this problem, I will talk about it in the next video. Now, how do we get the flux? I already mentioned that. You have to write the formula, the general formula at the beginning, which is the flux is equal to N B dot S. N is the number of loops you have, and since I have one rectangle, that means, or one square, because look at the figure. I mean, you have P, M, N, Q. It's like a square or a rectangle. You don't have way too many loops, like a coil. Okay, so N it's literally equals to 1. You can to not write it in the formula from the beginning, and you can write it as a general formula, then specify that N is equal to 1. So the flux is equal to B dot S only. Okay? When I say B dot S, you have to know that you have to find B times S, the surface, times cosine the angle between B and S. Now I know B is going inwards. We discussed that in the figure. B is going inwards. It has a circle with an X in it. But what about the surface? The surface, to know the vector of the surface, you have to use the right hand rule. Okay? You have to use your 4 fingers going in the direction of the positive direction chosen in the figure. Okay? So it will be going from Q till P till M till N. You have to rotate your fingers like this. And all the way, you would have your thumb going also downwards, also inwards the screen. It's not coming out your thumb from the screen, it's going in. So the vector S of the surface should also be going down the screen. Okay, so the angle between B and S is actually 0 degrees. Why? Because B and S, both of them are inwards. Okay, they have a circle with an X in it. Now, my first problem is gone. My second problem is B. B, they mentioned in the given it's uniform, so it's not changing. It's not my problem here. So B, it will be kept. This is the surface. What is the surface of a rectangle? Surface of a rectangle, it's the length of the rectangle times its width. Okay, now, let me look at the figure again. they have the distance from P to Q, they named it in the given small l. And they told you that the width is from Q to where was N at the beginning, the rod at the beginning. At the beginning, it was here. N at the beginning was here, just where I wrote N. Okay? And after a while, this length or this width of the rectangle, the width of the side, it's decreasing. So it was D at the beginning, and it's getting smaller and smaller by a value called X. So the length of Qn, it was D at the beginning, and it's getting reduced by a small amount called X when we pull Mn downwards. So it's minus X. D minus X. Okay, it was initially D, and we're decreasing that to minus X. So the surface here, we have a length that is called small l, it's not changing, but the width is changing. It was D at the beginning, and we're reducing that by small value X. Okay, so I have to replace the surface by that. Every time you have the surface changing a long time, you have to replace the surface. Your variable is the surface, so it should have X. So instead of the surface here, by the way, just to be clear, instead of the surface here, I will be putting small l times the width, which is minus D minus X. If you expand that, you will be getting BL times D, then BL times minus X. So it's BL D minus BL X. Is that what they want in the question 2.1? I think so. Yes. BLD minus BLX. If you had the other way around, if you had minus here and plus here, a positive sign before BLX and a minus before BLD, that means you confuse the angle. Sometimes people mess with the right hand rule. They don't know where actually S is going. Let's say you misunderstood and you did a mistake. You consider that S is going outwards and the angle in between is 180. Cosine 180, the whole thing here should be negative 1. So you'll get the opposite value of what you're actually solving, or what you're actually supposed to be solving. Okay, so be careful for the angle. Sometimes people confuse that. Now, cosine 0, by the way, it's 1. This is what I didn't write it again here, because anything times 1, simply it's anything. Now, in 2.2, deduce the expression of the electromotive force E induced in the rod in terms of B, L, and V. So we want to find E, and it's the second formula that you have to know, which is E equals minus B flux over dt, which is the derivative of what you already got in the previous question. What is the derivative of B, L, D minus B, L, X? The problem is you don't know. Sometimes people don't know what actually is constant and what is not. Okay, B is uniform. Uniform, that means B is a constant. It's not my problem, it's not changing. L is the length between P and Q in the figure. P and Q. This is not changing either, so it's a constant. Okay. D is the distance that we had at the beginning, and the distance we had at the beginning, it will always be the distance that we had at the beginning, so it's not changing. D is D. Okay, so it's also a constant. It's the original value that we chose to start from. This is not changing. B is uniform, L is PQ, also it's constant. So my variable here, it's X. Why it's X? Because let's go to the figure again. I'm taking M and the rod here in the middle with my hand and I'm pulling it downwards. That means the value of X here, it's increasing with time. When I pull this downwards, I'm increasing X. Let's say Mn is here. Mn will be here at some point. That means X would be from where it was at the beginning till the new, to the new position of Mn. Okay, so X increased. So it's the one that is actually changing. So X is my variable. Now, the last step is you have to find the derivative. B, L, D, all of them are constant, so their derivative should be 0. Okay, so the only thing that is not changing is the second term. Minus BL, they should be kept. And we have a minus before the derivative, so together they would be plus. BL, they are constant, so we will leave them alone. X is the one that is changing. And what is the derivative of X in function of time? And by X, I mean the position. I'm changing the distance of Mn from a point to another. In function of time, that is actually the speed. Okay, why? Because X is the position, and it's not any position, it's the position changing in a rectilinear motion. If it wasn't a rectilinear motion, as you know from 11s, I cannot simply just say that dx over dt is v. What if it's curvilinear? Then it's different. Dx over dt, it's something else. Now, plus b lv, and this is the e that I'm looking for. Okay. Now, 2.3. Knowing that UQP equals UC equals E. That means the electromotive force will be going, all of it will be going to the capacitor. Show that the expression of the current induced in the circuit is I equals CBL dV over dt. To take that type of question, I have to relate I to UC that they talked about in the given, which is equals to E. And when I say that, I don't mean just think about the electromagnetic induction. Why? Because they mentioned the capacitor, they mentioned C. They mentioned the capacitance C, so you have to think about the formulas you took in the capacitor chapter, which is, since they want I, and all I know in the capacitor chapter about I, it's I equals dq over dt, then be it, I can use that. And I also know in the capacitor chapter that Q is equal to CUC, the capacitance times the voltage of the capacitor. So I can replace the Q here with its formula here. It will be the same as CUC, and I will be getting the derivative. Instead of Q, I will be putting its formula CUC, okay? And C is a constant, so we will keep it outside. I will be having C DUC over dt. Now you tell me, why did you get this? Because they explicitly mentioned UC. UC, it's E. Replace UC by E, and you'll get to your point. I, it's equal to C dE over dt. UC and E, they are the same. Okay, and I already got my E in the previous question, which is BLV. Replace that here. So I will be getting I, C, the derivative of what I had before, which is B, LV. Again, every time you want to find your derivative, keep your constants outside. So B outside the derivative, L outside the derivative. So I equals C, B, L, and V is the speed of the rod, which is changing because I'm moving that rod, and it doesn't have the same speed all the time. So V over dt only for V. And this is exactly what they wanted. I proved that. Okay, now part 3. What I want to say is that we have an electromagnetic force now, since the rod is going up and down. Okay, and my job mainly is to answer the question, yes, but I have to know how the force F is going in the first place on the figure. Why is that? Because if I want to use Newton's second law, as they're saying in 3.1, I have to know the direction of F in the first place so I can continue. Okay, so here in this figure, I have to go back to the figure. I have the positive direction going from Q to P, and I know that the current is also going from Q to P. And why is that? Because simply E that I got in the previous question, 2.2, it's positive BLV. B is positive, L is positive, and V is positive. And we have a positive sign, so everything is positive. And since E is positive, I is positive in the electromagnetic induction. Okay, so I is going from M to N, not the other way around. So, and I know that B is going inward. So how am I supposed to know how F is going so I can pursue my calculations? Okay. You have to use your right hand rule. Your thumb should be going to the right from M to N. Keep your four fingers closed. Just use your thumb now. It should be going from M to N to the right. Okay, your second finger, your index, should be going like B, which is inwards. So put your hand in front of the screen, okay, and make your finger look like it's going into the screen, okay, while keeping your thumb going to the right. Then your third finger doesn't have any other option but to be going upwards. So F should be going upwards, just like T, the tension of the spring, okay, which is opposite to the x-axis that we have in the given. Okay, now we can start question 3.1 by applying a Newton's third law, a Newton's second law, I'm sorry. We have the forces equals to mx double prime I, with x double prime being the acceleration. Okay, because x is the position, its derivative, if we have a rectilinear motion, it's v, and the derivative of v is x double prime, which is v prime, which is a. I'm talking about the rectilinear motion here, okay? Now, what are the forces that we have? It's T, but by the way, it's not the same as T when the object was at equilibrium. In the first question here, we said that at equilibrium, K delta L0 is equal to mg. We label delta L0 for a reason, because this is the value that we have for the equilibrium condition. Here in question 3, we don't have equilibrium, so we have to simply call it delta L. But every time we see K delta L0 and mg, I can suppose them they are equal. They are equal, even if it's not the equilibrium condition. Okay? So, if it's not at equilibrium, you have to say in general T equals K delta L, but not delta L0. Delta L0 is for the equilibrium. Okay? But even though you don't have equilibrium in your exercise, and you see in the equation K delta L0 and mg, you can cross them out because they are equal no matter what the condition is. Okay, I think it's not clear now. When I solve the question, maybe it will be clearer. Okay, so T, Hooke's law, that is general, which is K delta L, plus the wave, plus the new force, electromagnetic force F. Now, by projecting on the x-axis, T is opposite to the x-axis, so minus T, W with the x-axis, so plus W, and F is, as we said now, it's opposite, so minus F equals mx double prime. Now, we have to replace each one of them by their formulas, so I will solve that on the side. T, it's K delta L. I didn't say delta L0 because it's not equilibrium here. But if I go to the figure, I can see that delta L is the distance, or it's the elongation of the string from where it was at the beginning, which is here, till where it is now. So from here to here, this is delta L, the new one. But if I cannot but relate delta L to delta L0 because they are on the same figure, I can relate them somehow. So delta L, it's delta L0 that we had at the beginning, plus a little bit of distance here that they called X. So delta L, it's delta L0, the elongation of the spring at the beginning. And by pulling the spring down even more with an amount of X, I cannot help but say that delta L is delta L0 that I had at the beginning and a small distance X. Okay, so here I have T equals K delta L. I can replace delta L by delta L0 plus X. Now this is that T. What about W? W, it's mg. This is easy. F, it's I, B, L, sine of the angle between B and L. And since we use the right hand rule, we're forcing a 90 degrees angle. So B and L, it's always 90 degrees, the angle in between them. And sine 90 is simply 1, so we can simply get rid of sine. And F, it's IBL. But what I want you to know, let me name it small l, because this is what we did for the previous questions. Now, what I want you to know is I is something that we know from the previous question. You cannot avoid that. I, it's CBL dV over dt. So let's replace that. I, it's C, B, L, dV over dt. This is I. And we just write the rest, which is B, it will stay B, and L, it will stay L. Now B and B, we multiply them. L and L, we multiply them. So it's C B squared L squared dV over dt. Now you might ask me, why are you solving this? They gave us this expression in the given. You are right, but they cannot give you this expression, okay? Because F, it has a formula and you're supposed to know it. It's either URLS or GS. Now, dV over dt, it's V prime, the derivative of V, okay? And I just said right now that the derivative of V, it's the acceleration, or it's x double prime, okay? So let's replace that. CD squared L squared x double prime. Now you ask me why? Because at أصلا in the first place, I'm solving to get a differential equation, and it's of the form x double prime plus something x. So I don't want to see v or a. I want to see x prime, x double prime, and x. So this is what I'm doing here. I got f, I got the weight, I got t, and it might be a little bit hard for you to understand why I replaced delta L by delta L0 plus x. But again, I'm supposed to have x in my expression. So I have to relate delta L to the values that they mentioned in the given. Delta L is not mentioned in the given. What's mentioned in the given, it's delta L0 at equilibrium, and x, the small amount that we elongated the string with. Okay, so minus t, it's simply minus k delta L0 plus x. W is mg. F, it's minus b squared L squared c double prime equals mx double prime. Did I forget something? cb squared L squared x double prime. That's it. Now expand, remove the parentheses. Okay, so we will be getting minus kx plus mg minus v squared L squared c x double prime equals mx double prime. Okay. Now, when I went back to the first question solved, I told you that we have K delta L0 equals mg, and this is always applicable no matter what you're working on. Even though it's a condition that we got at equilibrium position, but that doesn't mean this equality is not true for anything else. It's true. Okay, you cannot say in our case, when it's not at equilibrium, you cannot say that K delta L equals mg. Yes, this is wrong. Okay, but if you say delta L0, this is right, because it's true. They were equal when it's at equilibrium and when it's not. They have the same value. Okay, so what I mean by that is like I noticed that I have K delta L0 and mg, and since they are equal, and let's say mg is 10 newtons, then K delta L0 is also 10 newtons, and one of them is negative and the other is positive, so they cancel each other out. And we will be left with the x, and this is what I really want. Minus kx minus b squared L squared c x double prime, and I will get m to this side, so it's minus mx double prime equals 0. Now, take x double prime as a common factor. We cannot have two of the same value. Let me just also remove the negative signs. Minus, minus, minus. They can be removed since all of them have this sign. Okay. Now we will be getting kx plus x double prime as a common factor. Now we will be left with b squared L squared c plus m equals to 0. Now, as you always hear, keep x double prime by itself. I don't want the coefficient next to the derivative. So you divide the whole thing by that coefficient. You divide the whole thing by the expression that is next to x double prime. So you will be left with x double prime alone, which is what we want, plus k over the value we divided with, which is b squared L squared c plus m. X equals to 0, and this is supposed to be the differential equation. It's not so hard. They told you to start with Newton's second law. If they didn't say that, it might be a little bit hard, since some of you are not familiar with how to get a differential equation from Newton's second law. Okay, but since they gave you the way to solve and try, It shouldn't be that hard. The only tricky thing is for you to notice that minus K delta L0 and mg can be cancelled out. And the only things that we want is x double prime and x. So you have to show that in your calculation. Now, since the question is cut out and I don't know what the expression is, let me just check. There it is. Yep. X double prime plus K over M plus B squared L squared Cx equals to 0. Okay. Now, 3.2. Specify the nature of motion of the rod. Nature of motion. It's a simple harmonic motion and it's free. Undamped because they told you there's no friction and it's free. They mentioned that in the title of question 3. There it is. Free oscillations. So it's free undamped oscillations. And what is the nature of the motion? It's a simple harmonic motion. Why? Because the differential equation that you got, it's x double prime plus something which is a constant, x equals to 0. And this is of the form x double prime, which plus omega 0 squared x equals to 0. And this is a simple harmonic motion. So you have to rewrite the expression, of course. You don't just say blah, 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 like I did. And you say that it is of the form, x double prime. You explain yourself. So it's a simple harmonic motion. Now, 3.3, deduce the expression of the proper period T0. Okay, this is really simple. T0, it's 2 pi over omega 0. Omega 0, obviously I just mentioned that omega 0 is the value before x. Now what is the value before x? Using the differential equation, it's k over m plus b squared L squared c. I just got that in the previous question. So what is omega 0? It's radical of this value. And don't you try telling me that we have a square so we can keep them outside. You cannot, because you have a positive sign in the middle. Okay? Things are a little bit complicated when you have a plus sign or a minus sign, when you have fractions, radicals, and all of that. Now, since we got omega 0, just replace it here, and we will be having T0 equals 2 pi over that thing. When I say over that thing, I mean find the inverse of that, but let me be specific. K over m plus b squared L squared c. When you have over a fraction, just inverse the fraction. Instead of saying k over something, you say something over k. You inverse that. So you will be getting 2 pi as it is, and the inverse of whatever you have in the radical. And this is the T0 they're asking for. Now, the duration of 10 oscillations, and when they say oscillation, that means you have, let's say, a wave. Okay? The distance between 2 peaks, or yeah, let me say distance. Yes, this is one oscillation. So when you go down the hill and back up to the same point, this is an oscillation. Or when you go from the point in the middle all the way up and down back to the same point at the same level, this is what we call an oscillation. So you have 10 of them now. The time for 10 oscillations is 4.69 seconds. And since it's free and undamped, that means the oscillation is repetitive. It's the same oscillation that is repeated all over again. When we have GS students know that when we have a damped oscillation, that means we will be having up and down, then it will decrease over time like this. This is where things change for me. But since there's no friction here, so I'm repeating the same oscillation all over again. Okay, so I have 10 identical oscillations that took 4.69. Since they are identical, I can find the time for one of them. The time for one oscillation should be 4.69 over 10. I divided by 10 because they are identical oscillations. If they weren't identical, you cannot divide by 10. And by identical, I mean there's no friction. And it's a free oscillation. It's free on damped. If it's forced, no. And if it's damped, also no. You cannot do that. So the time for one oscillation is 0.469 seconds. Now, I didn't even read the question, but I cannot help but analyze what I'm reading in the given. So determine the value of B knowing that M equals 10, L equals 10, C equals 8, and K equals 1.8. So let me just rewrite the given because nothing is an SI. M is equal to 10 grams. Convert that. So we divide by 1,000. L is 10 centimeters. We divide by 100. And a lot of people confuse that. The centimeter to meter, we divide by 100, not 1,000. And from C equals 8 millifarad, we go to 8 times 10 to the power minus 3 farad. And K, it's an SI that's grade 1.8 Newton per meter. Now, they give you all of these values because this is the value of the period that we got and the omega 0 that we got. T0 is a function of M that they gave you. B, they're asking for it, so I will keep a question mark on B. They give you L, C, and K. Okay, so you're left in this formula with T0 and B. Now, T0 is something that I already expressed when I read the idea of the oscillations. T for 10 oscillations is 4.69. The time for one oscillation, which is the same as the period. If you read your course really well, you know that the time to go from one oscillation or to complete one oscillation, this is what we call the period. Period T. It is the time to complete one oscillation. You cannot say distance, it's the time. It is the time to complete one oscillation. So since the one oscillation took 0.469, so we know T. We know T0. So T0 here, we can remove its question mark. We know it. So I can get B from that. Now, a lot of students confuse that. Teachers like to get an expression first, then you replace this expression that you have, or the values that you have in the expression with the numbers. So since they want B, find an expression for B first. Do not replace everything with numbers, then confuse the numbers, then I don't know, the teacher cannot correct properly your paper. So T0 equals to, this is for 3.4. T0 is the value that I will be using. And I want to find B. So we have to take all of the values to the other side. But to do that, first I have to find the square so I can remove the radical. So square, and we remove the radical. Okay, now we take everything to the other side. So we will be starting with 2 pi squared equals M plus B squared L squared C over K. Then we continue with K. K will be multiplied on the other side. So T0 squared K over 2 pi squared equals M plus B squared L squared C without a square. Now M to the other side. So I will be getting T0 squared K over 2 pi squared minus M equals B squared L squared C. Now L squared and C are multiplied by B, so they will be divided on the other side. So T0 squared K over 2 pi. And next to 2 pi squared, we will be having L squared C minus M over L squared C equals B squared. Then to get B, we have to put the radical for the whole thing. And this is simply B. Okay, now you replace with the numbers. You will be getting B equals radical. T0 is 0 point, I got it in this question actually when I was analyzing it, 0.469 seconds. So 0.469 squared. K, it's 1.8 over 2 pi squared. L, it's 10, yep, 10 times 10 power minus 2. Then, and L has a square, so we will be putting square on the whole thing. Now times C. C is 8. C is 8, yes. 8 times 10 to the power minus 3. I'm done with the first fraction. The second fraction is the mass minus the mass, which is 10 times 10 power minus 3 kilograms over L squared, which is 10. This is L. Since it's L squared, we have to put a square on the value, times 8 times 10 power minus 3. This is the capacitance. You put it on your calculator, you're supposed to get something in function of Tesla. And since I don't have a calculator now, let me get the answer from here. So it will be 0.699T or 0.6 if we substitute the precise value of pi. By the way, replace pi by pi on your calculators. Don't put it 3.14. Okay, so the answer should be 0.6 Tesla, and that's it. It might look like the hardest problem in the official exam. It's a little bit tricky when you're solving, if you don't think in the right direction. But I think now you can get and understand how things can be merged into one exercise, because here you have a differential equation like you do in a mechanical oscillation problem, and you also solve something concerning the capacitance, and you also solve the electromagnetic induction using the right-hand rule. Either it is to find the direction of S if it's going upwards or downwards, and by S I mean the surface, if you forgot that we just got here. No, not here, here. Here, when we were solving the flux, we had cosine 0. We knew it's 0 because on the figure, they gave us the positive direction going from Q to P to M to N, and using our 4 thumbs, we knew that N is going inwards. I was just making sure, okay? And using the right hand rule in the first way, which is using the 4 fingers for the current and the thumb for S, the direction of the surface vector. And then we use the right hand rule to know F, how F is going, the electromagnetic force, using the thumb for the current, B for the index, and the third finger for F, the electromagnetic force. Okay, so this should be easy by now. Thank you for watching. Please subscribe, share, like, comment your questions, comment your feedback. I would like to see some criticism, I think. And thank you for your support. I hope you liked the video.